All right. We're going to look at reaction quotient and the chatliers principle. So we're putting things together. So if a mixture contains both reactants and products not at equilibrium, how can we determine which direction it will proceed? So what this is saying is that it's not at equilibrium. Is it going to go towards the products, towards the reactants based upon what we know? We got to compare the current concentration ratios to the equilibrium constant. Concentration ratio of the products raised to the power of their coefficients, just like in the equilibrium expression, is called the reaction quotient. Now, let's say we got gases. Reaction quotient, constant. We could have it in concentration form, or we could have it in pressure. We set it the same way, but again, the concentration values are not necessarily the same ones that are found in equilibrium. Okay? So we got to keep that in mind. Always keep it in mind that the quotient's not the same as equilibrium. It's a little different. If they are the same, we got equilibrium. If there's a higher Q value than K, that means there's more products than at equilibrium. The system shifts to the left, consuming those products, forming more reactants till equilibrium is achieved. So again, shifting towards the reactants. If Q is less, that means there's more reactants than at equilibrium, means it's going to shift to the right in order to get to equilibrium. So keeping these straight, kind of tricky to keep that in mind, especially in the middle of an AP test. That's what you have to understand in order to think of which way it's going to shift one way or the other. So what this kind of looks like, if Q is greater than K, the reaction will proceed fastest in the reverse direction. So as we see with this little graph over here, if we started off with a whole bunch of A, no B, we've got Q is infinite, right? Your B over A, 1 over 0, doesn't exist. I should say the opposite of that, B over A, which would be 0. But as it increases, Q is going to be getting larger, but is less still than K. So its reaction is going to run to the right. When it's equal, we're going to be at the equilibrium constant, and the reaction is going to be the same. However, when Q is greater than K, reaction is going to run to the left. We're going to have products become reactants. If Q is less than K, it's going to proceed fastest in the forward direction. Products increase, reactants decrease. Because again, one of the things students often overlook is that when you make products, you have to use up reactants. When this goes up, this goes down. Sometimes students will keep in mind, they go, oh, more products are made, but not keeping in mind how much that affects the reactants themselves. If K is Q, it's already at equilibrium, no change. Everything stays the same. Likewise, if we look at the other spots on this little graph, if a reaction mixture just contains reactants, nothing's reacted yet, Q is 0. We have not reached equilibrium. Actually, I should say, we often think of K is equal to Q at equilibrium, but it hasn't reacted, so it's still less than K, so it's going to continue forward. Remember, your K value cannot be negative, so if you start off at 0, the only way to go is up, meaning the forward direction. If the reaction mixture contains only products, then it's infinite, because then it would be 1 over 0, infinity, undefined, whatever, and then it will only produce stuff in the reverse reaction. This could be, you think of, well, how can that occur? Well, let's say we have this reaction, but let's say we know this relationship. We know this relationship here. If I just have B in a container, some of that's going to immediately start to break down and make A. It's the exact same idea when we start off with only A as our reactants. So let's look at a couple of these in example. So we've got our balanced equation, and we have our K. We can see our K is very high, so that means we're going to have very little of these, much more of these. We got our reaction concentrations, blah, 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 blah. Determine the direction the reaction will proceed. So this is like a snapshot in time. Okay, this is not at equilibrium. This is a snapshot in time. We're either above it or we're below it. We have to make our reaction quotient, making sure we get all of our coefficients. plug in our values, making sure we use our calculator correctly, and we see Q is very small compared to K. That means it'll move towards the right, moving towards the products. Still more products to be made, still increasing from 0, where we started off at. Another example, we've got some different things here. Certain temperature, it's very small, but not 0. A reaction mixture containing the solid has blah, blah, blah. Will more of the solid form, or will some of the solid exist and decompose as equilibrium's reached? Now, this is kind of a confusing question because of the fact that we think of, well, increasing more of this is not going to change any to make our equilibrium reached. But if we have more of this present, we will have higher concentrations of these or higher pressures, okay, present. So we plug in our Q value. We have our molarities, concentrations. We see this is our Q. Kc is this. Q is higher than Kc. So that means it will shift to the left to make more solid form. Again, this is just to make it go back to equilibrium. It kind of makes sense because if this breaks down to make more gases, if we have higher gases, that'll make more solid because this is in a equilibrium balance, much like when we think of solubility equilibrium with this solid dissolving into aqueous solutions. So again, what we're doing here is throwing in some calculations in order to see how these compare and knowing which way it'll shift based upon those. Come in with any kind of questions and I'll take care of you later. Bye-bye.